of you have seen the sculptures on either side of the pedestrian bridge at University Avenue in Berkeley. Those are epoxy and metal powder. So, and they've been out there for probably, what, about 15 years now, maybe 20. So, you know, these things will hold up quite well outdoors. So a lot of times when we think of product that's going to be outside, we don't generally consider epoxy because it breaks down. This piece was put outside for about, I don't know, 6 months or so, and it's gotten very yellow. So we don't usually think about those kinds of things and putting them outside. But what I'd like to do before we really delve into it is maybe do a quick little demo with some fast-setting polyurethane. Peter was good enough to provide us with a alginate mold of somebody's hand. Normally we don't recommend that you pour resin of any kind into an alginate mold because the alginate is so reactive to moisture that, and we'll talk about that a little bit later, so reactive to moisture that it won't set properly. It may tend to foam up, may tend to be gummy, may tend to be all of the above. But this particular product, and there are a number of them out there, this particular product, Smooth Cast 300, made by Smooth On, our friends in Pennsylvania, is a fast-setting version. I think it sets in about 3 minutes total. So again, we have two components here. We have an A and we have a B. And we'll talk about the difference of how the A's and B's of each of these systems differ and why they do what they do and how they do what they do. But we're going to do a quick little casting here just to see how this all works. In the old days, before this resin came along, we do a lot of business with taxidermists. Taxidermists are very creative types. In case you've never had to deal with a taxidermist before, they can be very creative. And one of the things that they discovered is that an alginate mold is a very good way to capture the image from a reptile, for example. You got snake skin, you got scales, very fine detail. And so they would make an alginate mold, but then they couldn't make a resin casting from that mold because none of the resins that we had at that time would work. But what they discovered, you take regular polyester resin, blend it with Bondo into kind of a slurry because it'll set so fast. You can mix that with the appropriate catalyst, pour it into the alginate. It'll set fast enough that it's not going to react to the moisture. Now, if you did that with regular resin, you'd have a foamy, gooey mess on your hands. But the Bondo sets so fast that, again, it doesn't have time to react to the moisture. So we sometimes use that technique as well, in addition to this one. But this one is just easier because, as you and I both know, artists hate math. Come on, admit it. You guys hate math. That's all. We've tried to create some systems that are relatively easy to use. When I say we, the people at Smooth On, I'm not that smart. But they've created some systems that are very easy to use. So all you have to do is mix one part of A and one part of B by volume. Wow. No scale, no measuring. Just do it by eyeball. Are you kidding me? They always say on all their containers, mix thoroughly before use. It generally means something when they say that. But in this case, just because of experience, I know that sometimes the B side of these systems may have a tendency to separate. There are some chemistries in there that will fall out of solution or suspension, and so they will sometimes need to be mixed up. So I just give them a mild shake. The A side, on the other hand, we don't see any separation there, so we can just pour that right out of the container. Now these are both going to be clear to start with, and you'll see what happens when they set. So I'm literally just doing this by eyeball and measuring by guess and by golly. So we're pouring 2 equal volumes of material into 2 like or same sized cups. That's important so that when you measure, you get an equal measure. And then there are 2 ways you can go. If you use cups that are big enough, you can pour 1 cup into the other. If not, you just get a 3rd cup that's big enough and you pour both of these into 1 cup. Now, once we have put both these chemicals in here and we've mixed them, the clock is ticking. And so we can't fool around. So you can see I haven't put part A in yet. I'm a coward. The other thing is polyurethanes, and we're going to kind of jump all over the place here. Polyurethanes are very moisture sensitive, which I think I've already mentioned. So generally speaking, when I'm using polyurethanes, I might not use a wooden stick, but in this case I'm gonna fake it. Wood will contain a certain amount of moisture depending on your ambient conditions. In Arizona, probably not much. In Louisiana, different game. So if you're going to mix this with a wooden stick, you're going to be stirring moisture into that resin as well. What's going to happen if you put moisture in your resin, she says? Well, it's going to cause it to foam up, and you're going to get bubbles in there. And we'll see some of that here, and I'll show you how to address that, and we'll look at some of these castings so you can see what the moisture impact shows up like. Okay, so don't distract me, Peter. Okay, go ahead. Yeah, it's already getting warm. I can feel it getting warm in my hands, and if I wait too long, we've got 30 seconds of pot life, supposedly. I should have looked at the clock. But it's important to mix, scrape down the sides, and just get it poured, because if we don't...
Because it's so liquid, it mixes pretty well. I mean,
it does.
Like a gluey epoxy that
yes.
much more careful.
So I'm going to pour the excess into this little mold here. We'll give you souvenirs to take home, share with your family. Sometimes if you wait too long, sometimes if you wait too long, this thing will set up mid-pour. This is polypropylene. These will handle the heat just fine. But there are certain, like if you look at the bottom of a drink, like a water bottle, it'll say PETE or PETG. Those are not very... Bubbles can be a problem. But a bubble is if it's an airlock, it's a physical problem. It's not a chemical problem. Bubbles are typically a function of a physical airlock in the mold. So if you think about the space, the negative space that you're looking at, you have to think about what's down inside that space. If you've got a space that actually forms an airlock, you're going to have trouble getting the resin to fill. Sometimes what we can do, and I didn't do it here, we can pour it in, kind of pour it halfway and then slush it around a little bit, and then pour the rest in to capture all those little areas. But that's, as I say, it's just generally a physical problem. This has set, so if you want to take a look, it's set hard, so we can now demold this thing. If you wait overnight for a polyurethane to cure completely, oftentimes that surface is going to be so tight that the new material won't adhere to it. So getting back to the basic mechanics of how these systems work, they all have two chemicals that you mix into each other to create a chemical reaction. Now the difference between the three systems is that the polyester, as I indicated earlier, uses a catalyst. A catalyst, if any of you can remember your days in high school chemistry, yes? A catalyst is a material that aids in the reaction but is not consumed in the reaction. So what does that mean? Well, what that means with polyester is that you can get away with murder. In other words, you take this basic resin, you put in 0.5% catalyst, 1% catalyst, 2% catalyst, 3% catalyst. It's all going to cure as long as it's mixed reasonably well. It's just going to cure at different rates. So you're changing the dynamics of how that material is going to cure based on the amount of catalyst you put in there, as well as the mass and ambient temperature. So if you have a large mass, like our hand here, that's a fairly large mass, or this, that's a fairly large mass, you generally want to reduce the catalyst to compensate for the fact that you have a large mass that's going to generate some heat. Well, maybe we can have this lovely young lady unearth the treasure here. Here, I'll give you a knife. You can just slice that off with. So while she's doing that, we'll move over to epoxies. I'm sorry. As stated earlier, with polyester, we have a catalyst that goes in there. The catalyst is not consumed in the reaction; it just aids in the reaction. So the way I like to think of it is in terms of dancing. You know, you've got dancers in a ballroom. In the case of polyester, the catalyst is the busybody that goes around and grabs two kids and brings them together and says, here, you dance together. You have to dance together. So that's what the catalyst does. When we move over to epoxy, we have a different situation. We have a resin and we have a hardener, but they're used at a very different ratio. In this particular case, it's 2 to 1. And in this particular case, it happens to be 2 to 1 by weight. So in this instance, you'll have to get a scale to measure it accurately. Unlike with polyester, there is a range of the catalyst at which the resin will react. Usually it's about 0.5% to 3%. With epoxy, you have a very specific ratio. You have to mix part A and part B. So you can adjust for temperature with more catalyst, whereas with epoxy, you can't do that. So here, let's take a look at that hand. Ah, not bad.
Not bad at all.
Not bad at all. Came out pretty good, all things considered. So
Resin was
this is a smooth cast 300Q for quick. So it's very fast setting resin. But getting back to epoxy, with epoxy, going back to my dancers example, with epoxy, the dancers all have to be intermingled as partners, okay? Nobody's going to come in and help them. You have to be the one that helps them with this. And that is, you have to really stir it and mix it thoroughly to get all those dancing partners intermingled so they can connect. And polyurethanes as well. You have the same situation with polyurethanes as you do with epoxy. You've got a fixed ratio of part A, part B. If you go outside that ratio, in this case 1 to 1, you're going to get some unpartnered dancers, if you will. So some unpolymerized resin. And so it's going to be either soft or sticky. And it may never cure. I mean, you may have a situation where you've got some product that's been sitting for weeks and weeks and weeks, and it's still soft, and you're going, why isn't this hardening? It's not going to. So it's really important that when you buy a product, read the instructions that are included with that product. If you have enough time, sometimes we do a 2-bucket mix, where if you got a big enough batch and you want to make sure that everything is really thoroughly incorporated, all those dancers have to be intermingled. And if anybody's left out, they're going to be left out. They're not going to cross over across the room and connect with this person over here. They're just going to be left out. So if you have 2 buckets, you can mix in one as well as you think you can. Pour everything into the second bucket, scrape it out with your stick, mix it again, and then pour it into your mold. Some of these materials drill and machine easier than others. Some of them polish quite nicely. If we look over here at my friends, the polyester, and I have a special kind of a, I don't know, place in my heart, I suppose, for polyester. We've been around so long together. This is a rose, dried, because the polyester doesn't like moisture. It's been well dried, and I cast it in layers. I embedded it in layers in a tin can, and then I peeled the can off, and then I started to polish it. And you can see where there's some sanding done. You can see where there's some polishing done. You can bring it back to an optically clear surface. Here, let's pass that around. So, you know, oftentimes I use containers that I find for doing these embedments. This was just a plastic cup. This was a little hummingbird that died in the warehouse, so I embedded it in a chunk of resin. This is a raw, unsanded, unpolished, machined chunk of resin, whereas this one, which was also cast into some kind of a package for a hard drive, I think. And so this rat invaded my kitchen. I said, you dirty rat. And so I dried him out thoroughly and put him in this chunk of resin here. And there he is forever. Because I often get students who would come in and say, can I embed my pet cat in resin? Well, you can, sure, but you just got to be very dry. So polyester is a great one for doing clear castings and clear embedments, but we can also do that with epoxy. This is an epoxy resin that was poured into a plastic mold. You can see the layers if you look at the side. They generally are going to be visible if you know what to look for, if it's been poured in layers. And this is a stone. So stones and hard objects are particularly difficult because all of these resins will have a tendency to shrink a bit. And if we talk about shrinkage, polyester is probably 6 or 7%. Epoxy is probably half of that, 2 or 3%. Polyurethanes, depending on the system, maybe even less than that. These things are easily colored, but they usually require resin-specific colorants. So in other words, if you're going to use polyester resin, you want to use a tint or a dye that's going to be acceptable to that system without altering the chemistry or creating some imbalance in there that would prevent it from curing completely. But we have a whole series of dyes, various colors, lots of different colors. Pink, you know, you want to make a pink angel? We got pink angels. We have pigments that you can use in epoxies and polyurethanes, but especially when you get into epoxy and polyurethanes, it becomes even more resin specific, and if you don't use something that's going to be compatible, you can really upset those dancers in there. They're not going to want to dance together, they're not going to want to connect, they're going to want to kick out that extra whatever it is that's in there, and you're going to see a residue on the surface of your casting that's not going to be very pretty. So these are the kinds of things that you have to be wary of. You're going to start putting in colorants and fillers and embedding things. You do have to think about chemistry at some level, but the point that I was getting to was that if we, again, look at all these different castings that are on the table here, you can really do just about anything with any of these materials. It's really a matter of the pathway that you take to get through the process. If we look at these two castings here, these are polyester done with mineral fillers. This was filled with chalk. Just, you know, the same sort of thing that we wrote on that chalkboard with. It's calcium carbonate, it's whiting, it's chalk. It's all derived from the same kind of thing. It's a stone that's pulverized and then sifted. It's a fairly bright white color. I put some additional white pigment in here with a little bit of marbling to create kind of a marble effect. This happens to use a filler that is translucent. We use this a lot for doing synthetic onyx, what's the other? Onyx jade is another one. And so if you hold this up to the light, you can actually see some light transmission. So a lot of times I get students that are going, how can I make something that has that kind of light diffusion characteristic? Well, this is one way. So you can put a filler in there. Another way is by physically abrading the surface and giving it kind of a frosted glass effect. So if we took this and kind of either give it a light sandblast or scuffed it with a Scotch-Brite pad or something like that, or some fine wet and dry sandpaper, we could achieve a kind of a glow to that. If we lit it from underneath, it would just kind of glow because of the nature of the resin. So the light would diffuse through there. If we take any of these base resins, we can also incorporate metal powders into them. So if we look at this piece here, it's got a little bit of everything. This one happens to be polyester and fiberglass, but we've got atomized bronze, brass, steel, aluminum, copper, zinc. If we look at this casting, it's a similar kind of deal. This was actually done in a classroom where I had the students brush in one section of each. Unfortunately, we lost part of it here. But what you can see is that the layer of metal that's here is really very thin, and the backing is more resin that's been filled with, in this case, chalk or calcium carbonate, because it's cheap. So that's another way you can create, you know, a sculpture. This is done, you know, same idea. This was done with bronze in a polyurethane resin. So one of these clear polyurethanes.
Bronze powder.
Yeah, bronze powder, atomized bronze. So it was this type of resin that was then infused with the bronze powder, and then a layer was rotated inside the mold. So you've got a thin layer, and then it was filled with foam. So this is actually hollow. So you can pass her around. Be very careful. Don't drop her.
2 hands, please.
We rotated the mold. So it was a closed mold. So we had a closed mold. We poured it in, rotated around. A heavily infused bronze layer went into the surface. And then when the piece was extracted, the flashing was cleaned up much the same as you would clean the flashing or the you know, mold lines on any wax part or even a bronze part after the fact. It was chased, essentially, and then we applied a chemical patina and a wax sealer on there. So it's got a colored wax over the top of it. So there are a lot of possibilities. This, again, this is a bronze in happened to be a white resin. So you can see here where some of the white showed through, where there wasn't quite enough metal powder. But if we take this bronze and abrade the surface, because bronze by nature will tarnish just from, moisture in the air, people touching it, and so forth. But if we take this bronze infused resin and work that surface with a little bit of abrasive, you can expose the metal, and then you can apply a chemical patina to that and put a preservative on it, just like real metal. And the nice thing about this product is, even in the case of the epoxy, where these things don't hold up that well outdoors, you're going to see not only will the epoxy yellow, but it will get chalky in relatively short order. The metal powder, because of the nature of metal, it's absolutely opaque to the sunlight. So it's going to protect the resin that it's bound with, and if you got enough metal in there, you're going to have a long-term protection, and it does very well. We've seen many pieces out there that have been in the environment for approaching 30, 40 years now, and they still look very good. So all indications are that we've got a winner. So this is an opportunity, oftentimes may have been the case with Lou where a client wants a bronze piece but can't afford it because it costs tens of thousands of dollars, whereby you can create something that looks very much like bronze because it is in fact bronze. With bonded bronze, you can get away with much larger pieces and just do it much more effectively, much more efficiently. Now, epoxies are unique in that we use them for a very broad spectrum of applications. This is a coating epoxy. You guys who have seen, decoupage, sometimes we'll see that stuff. It was premiered in the 70s, I think, and it's very popular nowadays for just embedding images onto a substrate of some kind. We also use epoxy as an adhesive. There are a lot of epoxies out there that we use as glue, just because they flat out stick really well. And there are so many additives that you can put into the epoxy systems to enhance the adhesion. And so that's why I call epoxy sticky. And you're going to remember that because that's what we use epoxy for mostly. When we get to polyurethanes, they're in kind of a unique situation because the numbers of products that are out there in the environment, or in the marketplace, I should say, are quite numbered and quite varied. If we look at these rings of materials here, and if you take these products and just look at them visually, maybe bend them a little bit, you can see that some of these are a little bit flexible. So the urethanes kind of cover that gray area between rubber and resin. There are some of what we call elastoplastics. So they're not really elastomers, they're not really plastics, they're somewhere in between. So they have a little bit of flexibility to them. So what that enables a person to do, if you're making an engineered part that needs to perform on a physical level, you can create something that's going to will take a lot of abuse, will take a lot of heat. They can generate products that will create or take a fair amount of heat and withstand the heat and not deform. A lot of these materials, even after they've cured, will deform by the application of heat. So if we take this resin here and we heat it enough, even though it's been set for months, if we heat it enough, we'll achieve what's called the heat deflection temperature. This one, the heat deflection temperature happens to be about 125, 130 degrees. So if you're making a piece that's going to go out to Black Rock Desert and spend the weekend at Burning Man, you better make sure that it's built properly, otherwise it may get a little soft and sag under the hot desert sun. And that's true of a lot of these things, while there are other materials that have been formulated specifically to withstand the heat. This particular product will take a lot more heat, and it won't soften and bend like some of the others will. I'll just pass those around. So we can do pretty much anything here with any of these materials that you might want. Embedding, coating, casting, they can all do all of those things. Some better than others, and that's why it's important to think to the end of the process before you make a decision. In other words, are you going to do cold cast bronze? Okay, fine. Here's what you might want to look at, and then you can make a decision. Are you going to do a clear embedment? Okay, fine. And here's what you might want to look at. Are you going to do a coating? Okay, fine. Here's what you might want to look at. So it's really important to evaluate the whole process in its entirety, not just the mold making aspect of it. And the mold making aspect is important. You want to make sure you use the right mold material that's going to give you the best mold life in terms of what you're going to be pouring into that mold. Okay? So whenever people come in and ask me, okay, what's the best resin, mold material, whatever, I always kind of encourage them to go all the way to the end and work their way back, because that's going to really help to indicate which is going to be most appropriate for their application.